Thank you very much, Nick, for the kind introduction. I'd like to thank the organizers for the kind invitation. Oh, yeah, here. Thank you. Yeah, excellent conference, excellent selection of speakers. And so my talk will be about nanostructures composed of biomolecules, plasmonic nanocrystals, and semiconductor nanocrystals. And I am a theoretical physicist. So I do analytical models and also numerical models and computations. And here are my collaborators, my postdoc, my previous postdoc, Munich team, Tel Aviv team, Stuttgart team, Dublin team, and Nick Kotov, who is the chair of this session. So idea is very simple. So if we take nanocrystals, plasmonic nanocrystals or excitonic nanocrystals, unless we work with clusters, they have lots of atoms. Nobody can calculate it with the DFT. So my business is to make physics models of nanocrystals, and I also take biomolecules and molecules as dipoles and combine them together in nanostructures, and we can make this nanostructures chiral if you like. And so I think this field of chiral nanocrystals was motivated by work on chiral clusters by Robert and by Thomas. And also there are maybe more people. Terry did very nice silver nanoclusters. But here we actually don't look really, in the nanocrystals, we don't look at atomic structure because they're too big anyway. So we consider them in using some more or less continuous models, either classical or quantum mechanical. And so chiral objects are objects not superposable on its image, and we are chiral. Most of the biomolecules are chiral. We're all chiral, so it's everywhere. It's a big motivation, and we can probe such chirality, how it becomes twisted in a helical line, on a helix, or in many other geometries, with circularly polarized light. And so circular dichroism spectroscopy is a famous type of spectroscopy when we have millions of small objects, chiral or non-chiral, and we send light, left circularly polarized and right circularly polarized, and they measure, or we measure, difference in absorption. So objects are at random orientations, and we need to make orientational averaging. There are millions of them. And if object is chiral, then this signal is non-zero. If object is non-chiral, has symmetry planes or center of inversion symmetry, then this signal will be zero in theory. So this is kind of a famous method to test chirality of biomolecules. The signals, circular dichroism signals, are typically very small, and we will see why they're small. But they are very characteristic. They show the geometrical, the conformational structure of molecules. This is different signals coming from different states of protein. And mostly biomolecules do show circular dichroism, strong circular dichroism in the UV, because of the structure of the atomic bonds, actually, chemical bonds. In the visible, typically circular dichroism is weak, but optical responses may be very strong. For example, we studied photosynthetic molecules that absorb solar light, but they still show very weak circular dichroism in the visible. This is because of sp3 and sp2 orbitals. So chirality is very important because of the chemistry. So drugs are chiral, mostly via chiral. The molecules interact with chiral biomolecules. So chirality must be controlled in the drugs. And this is an infamous example of a drug that created lots of problems, dramatic problems. It was in the middle of the previous century. Because it was one of the states, chiral states, was actually not good, was very damaging. It was used by pregnant women, actually, this drug. It's a typical example that people show the talks. This is theory of chirality. So chirality, circular dichroism, optical circular dichroism is a weak effect because we need to include magnetic field. It's not only the electric dipole moment, we need to include magnetic dipole moment in the molecule. And then the product, the circular dichroism is a dot product of these two matrix elements. And this equation is obtained after averaging of orientation of molecules. This is very important. So basically, when we include magnetic field, it means that we also, in some way, include a retardation effect of light at the size of the molecule. This is why it's small. But it is small, but it is very characteristic. It is everywhere. It's very interesting to look at. So my first simple idea was to take chiral molecule and then make it interacting and place it next metallic metal nanocrystal and see the interactions between these two objects. So we have lots of chiral biomolecules in nanotechnology. People have lots of nanocrystals. And nanocrystals are such plasmonic, gold or silver. And it means that they have very strong optical dipole moments because millions of electrons oscillate together when we excite them. This is enormous cross-absorption, cross-section, and also very strong scattering. So maybe these properties will be interesting to use. If you look at these two worlds of biomolecules that we like to use, this would be proteins or DNAs, these molecules that they use in nanobiotechnology. Of course, we don't like to take exotic molecules. We like to take molecules that can be used by many, many laboratories. And we look at the nanocrystals. Then such important molecules like DNAs, proteins, they don't absorb visible light. Especially DNA shouldn't absorb visible light. Then if so, we would not survive because of the defects. DNA carries information. And they absorb in the UV, and they show strong circular dichroism in the UV because they are chiral. If you look at nanocrystals, mostly nanocrystals are non-chiral, and I will discuss it. And they are very strongly absorptive objects. They are very strongly they are active in the visible, but mostly not chiral. And we can see that these two types of materials are not in resonance. They're strongly off resonance. Nevertheless, I like to join these two types, these two worlds. And model would be the following. And it turns out it is Fano model, or Fano model. So this is a biomolecule with a discrete transition. We can include more transitions. And this is metallic nanocrystal with continuum of states, continuous spectrum, because quantization is very weak and we have lots of electrons. We treat these electrons as free electrons, basically confined inside a box that kind of bouncing like this. So this model, we worked a lot with this model. It was a model, physics model, was introduced to describe the spectra, soft X-ray absorption spectra in helium, we worked in quantum dots. And now, finally, I applied it to biomolecules, which I thought was very crazy, because this model is a typical model for, it is one of the simplest models in quantum optics, although it's not very simple. So mathematics needs very careful attention. And this paper is very fun paper. It's a really famous paper with lots of citations. So what we do, I treat these states as a continuum of states. The molecule is treated as two-level system with magnetic dipole moment and electric dipole moment. We solve the equations of motion for the density matrix, all these quantum optics things. And then we look at the spectrum. And then, as a first simple example, I took short helix, alpha helix of protein, peptide. And this molecule has the following so-called dichroisms spectrum. This is the red curve, the black curve. Here, basically, a few types of transitions are involved. Normal oscillations, normal dipoles, parallel dipoles, and even some additional dipole. And it is black curve. And then when in my model, when I made it interacting with nanocrystal, we observed very simple effect that the spectrum has now additional peak. It is at the plasmon resonance. And physical explanation for this is the following. At this wavelength, protein doesn't absorb, of course. It's not absorbing object. But it still has induced dipole moment because it is dielectric object with chiral geometry. And plasmon here is so active, it creates so much electric fields outside that these electric fields actually react on this dielectric chiral object, and chirality becomes seen in the so-called dichroism spectrum in the visible. So it's it was my simple explanation for this. And of course, what we like to do. We take some molecules, important molecules of drugs or DNAs or something, and they mostly have so-called dichroism in the UV, and then we place them near nanocrystals, and we like to get the signals in the visible because it's easy to register for sensors, and we also want to actually amplify them, if possible, dramatically amplify. So this may be a possible way in the future to measure so-called dichroism of a single molecule, which was not done. It's not possible yet. So for this, of course, we place molecules in the so-called hotspots, plasmonic hotspots, the places where electromagnetic field become dramatically enhanced. Of course, even single nanocrystal is quite optically active. It creates enhancement of electromagnetic field in the neighborhood. But when electromagnetic field becomes squeezed between two nanocrystals, a kind of singular point, here amplification will be thousands and thousands. And then we place biomolecule in this position and calculate so-called dichroism. One can see that the signal from the original so-called dichroism signal is almost invisible. But here we got very strong signals in theory, and then this is a simple effect, so it should be observed. This is the structures from my friend Gil Markovich group, and they use this chiral molecule from people, from from our stomachs. And they observe such patterns, and one can see that here the original so-called dichroism of biomolecules is not visible in the spectrum because the concentration is too small. This structure is not controlled in geometry, but now we can do it very well. Some my collaborators can do with DNA origami. This is a very well assembled structure. This is DNA origami carpet. 2 nanoparticles are attached like this. Structural yield of such complexes is almost 100%. So they observed this, and they couldn't see already the signals from DNAs. What is also fortunate for us in this geometry is that only these dipoles, molecular dipoles parallel to the molecular axis of this structure are enhanced. This is in this way, in this direction we have field enhancement, but in this we actually have suppression. So some people think that aliens are also should be also chiral, maybe also chiral, and then they can be right-handed or left-handed. We don't know because of the symmetry of the world. This comes back to the slides of Thorsten. I should say this is interesting. Those are interesting topics to think about. But my main interests are in construction of new materials with unusual optical properties. And here are more examples of this plasmon-induced so-called dichroism, where I was involved with very well-controlled structures with DNA carpet and nanorods, then silver nanocubes, then lateral structures. And so it seems to be quite general effect and relatively simple. So another type of chiral nanostructures, of course, can be made only with plasmons. And here I was completely bio-inspired. This is a famous model by Moffitt. And it is alpha helix protein. Here, Frenkel excitons or molecular dipoles are on helical line, and they can move. The wave function is coherent superposition of single dipoles. If we calculate optical response of this system, we will see this bisignate shape, derivative shape, positive, negative. Now, instead of Frenkel excitons or molecular dipoles, we like to have very strong plasmonic dipoles arranged on a helical line and look at the optical properties. And so then we can start from non-chiral nanocrystals, spherical nanocrystals, and then we need to have at least 4 nanocrystals because 3 are always non-chiral. If you look at 3 flies that would move randomly in air, they cannot escape from the plane. They never escape from the plane. So adding another nanocrystal can make it chiral because this system always has symmetry plane through the 3 points. And individual nanocrystals are spherical, they are not chiral. Then we need 4 nanocrystals, and geometry should be chiral. It means that it shouldn't have simple symmetries like mirror symmetry or inversion symmetry. They should be in the way that if we take this molecule, we make a mirror image. We don't look at this, we simply look at the mirror image, and we make another object from the mirror image. Then we take this object, and we are allowed to move it, to rotate it like molecule in a solution, and we try to superpose it with this initial object, and we cannot. So it means it is chiral. This is how I do demonstrations exercises with my son, who is in the elementary school. But it took for me some time to learn it, to understand it. So we calculated different complexes. Most chiral complexes, of course, are helical. Why? We know that alpha helix protein has really strongly chiral molecule. Also, we know that random coil proteins still have strong chirality despite of randomness, despite of a lot of disorder. So, and then we also observe that this is a very delicate and weak effect. It depends on the sizes and the distances, because this effect comes from the interactions, like in the molecular circle dichroism theory developed so well for the molecular dipoles. So it is 12 power of the size of particle and 8 power of the distance between particles. So it's a kind of crazy analytical formula with this crazy exponent. The reason why it is so sensitive to the sizes and to the distances, to the sizes, we need bigger dipoles. When we have larger size, we have larger dipole. Dipole depends on the volume. But we also need interactions, and we need the magnetic moment, which should be created through the multiple interactions, actually. Should involve at least 4 nanoparticles to form a loop. And then it was clear that this is difficult to realize. It's so sensitive to the distances. So if you look at biomolecules or natural molecules, chiral molecules, they are all almost identical. Millions of them, but they are identical. So so-called dichroism got so famous message. So suitable message to make it probably would be DNA origami. And when people use staples, short oligos, short chains and long chains, they mix it together. And because of this amazing ability of assembly, pairing ability of DNA, they form various objects, various geometries. So this structure was done by my colleagues in Tim and Anton and collaborators in Munich. So basically, I didn't quite believe that such things can be realized within some reasonable time, because requirements are so tough on the quality of the sample. This sample has quality 95–97% of structural yield. Almost all helices have 9 nanoparticles, and they measure circular dichroism. And then this exponent almost killed our project, because they start assembly with relatively small nanoparticles, because it's difficult to assemble large nanoparticles. They probably repel or whatever. And signals were very weak. But then they did really excellent extension of this project that made this project successful. They did overgrowth in solution with silver or gold ions, and one can see that the size of nanoparticles increased while the general dimensions on helix are probably the same, because they are given by the DNA linkers. And because of this crazy 12 exponent, signals went really up. And this becomes really strong system for circle dichroism. And we also calculated it. We calculated it numerically, and we checked it that this system is stable against defects. It may be bending of DNA origami or removal of some nanoparticles. And so helix is nice. It's nice geometry for the circle dichroism. Thank you so much. So how much time I have? I don't have time, right? 2 minutes. Excellent. It is 50% of my talk, but it's okay. So there's so many interesting details. Super enhanced helix becomes not so nice, but circular dichroism goes really high. So if you look at the natural biomolecules, circular dichroism in the UV, in the standard units about 20, very strong circular dichroism. For materials that we designed, circular dichroism 10 to 7, 10 to 8. So we designed really crazy material with very strong circular dichroism. And physically, it is clear that we can do it because plasmons are so optically active. But at the same time, it is interesting that it is invisible. And so this nanostructures can be made, chiral system can be made with nanorods. They can be also made mobile, moving like nanomachines. By adding certain staples, they can create such motion. And motion is monitored by the circular dichroism by changing of by circular dichroism signals. So basically, my contribution to this field is that I developed mechanisms for this message, and I will come back to this message. So nanocrystals, the world of nanocrystals, mostly non-chiral, because these nanocrystals are made from mostly nice, simple, noble metals like silver or gold with many planes of symmetry. Then nanocrystals got strongly anisotropic, which is great for many, many things, but they are not chiral, non-chiral. So it's challenging to make chiral nanocrystals, but it's possible. In most of cases, we use biological molecules. We take chirality from biology, of course, because it's so. We may take it from liquid crystals, but we didn't work yet with the liquid crystals. So, and we calculated first this, such shapes, and then chemists told me, nobody ever will fabricate it. But now it's fabricated by many, many groups, different versions. And also, chirality can be abiological. This is or non-biological. It is work by Nick Kotov group. It is done from using deposition at angles. Double deposition at 2 angles make such shells chiral. Then I always wanted to work with some minerals. This is ore of mercury. Maybe the next material I will work with will be meteorite, I hope. So ore of mercury is a crystal with interesting history. Was mined for centuries, used as pigment and also as source of mercury. So sending to this cinnabar mines was equivalent to the death penalty. So, but the chemists do it. So, and this is another citation of Pasteur. I really like that Peter mentioned Pasteur in his talk. So he sorted nanocrystals by hand, using tweezer probably. Two states of crystals, of macrocrystals, small crystals, were sorted. Here, it is impossible to sort nanocrystals because they're just too small. And what they do, they start growth with small biomolecules. The direct chirality of this material, and this material is chiral, it's chiral, the crystal is chiral itself. And then they can get pure states. And sometimes shape is non-chiral, and sometimes shape becomes chiral. This is interesting ideas about transfer of chirality. Small biomolecule transfers chirality to crystal, and crystal may get chiral shape or not. It will depend on the conditions of growth. So on one nanostructure, they can create 2 chiralities by like motion, creating some small nanomachines, motion of nanorods. And so we can see flipping of circular dichroism. And circular dichroism is one of the very few methods that can show such motions. Another method is used a lot is FRET, first energy transfer, for the molecular tweezers. It is now even more popular because of super resolution spectroscopy. And so We may have chiral plasmons because of plasmonic chiral shapes and interaction between. We may have chiral excitons in semiconductor nanocrystals or of mercury semiconductor. We may have metastructures used. In this case, they use some biomolecules which are almost like food molecule. So we can use very cheap materials for experiments because food is cheap. But what is expensive in this structure is gold nanocrystals, of course. And then they observed also this transfer of chirality and mechanisms that is responsible for this. We think it is electrodynamic mechanisms in large systems. And this slide is for Peter. He used gamma. We used psi in this equations. And also, these equations are written here in different way, and it will be equivalent to the equations of Peter for small chirality. And this is simply chiral media can be treated. So in this paper, we solved lots of models. And I saw they are very artificial. For example, model chiral metal. So we don't have really chiral metals. But now we have chiral semiconductors and also chiral metals, because we can put inside or on the surface chiral molecules, or we can make chiral shape. We may do some other things. This is shells. Continuum media approximation through the Xi. This would be oriented shell of peptides, of biomolecules, or non-oriented shells. We also have this in the experiments. So to conclude, yeah, this is a fun field. So this feeling that we are doing something really new and interesting. So molecular chirality and so-called dichroism is well established and famous field. But when we bring it to nanostructures, we have different excitations. Instead of Frenkel excitons, we have Wannier mode excitons. We have plasmons. Molecules don't have plasmons. We can interact non-chiral plasmon with chiral biomolecule. We can do larger nanostructures. We can amplify chirality, so-called dichroism of biomolecules. Thank you very much.
Like to ask, first one about have done. Yes, enough.
Yes, please.
In the plasmonic slides, you showed that when there are 3 nanoparticles, it's not chiral, right? So if we take 3 nanoparticles of different sizes, say 10 nanometer, 20, and 30, the center of the particles are not aligned with the same plane. So can that be a chiral structure?
It is still non-chiral if they are spherically symmetric. Why? Because then what we can do, we can just make 3 dots, 3 centers of nanoparticles, and we make plane. We cut planes through these 3 dots. And then this system will be non-chiral, will be symmetric against this plane. But with 3 objects, of course, with 2 objects, we can do chiral system if you take 2 nanorods. Good question. Please.
What chiral exciton is?
Chiral exciton. So there are 2 types of chiral excitons. So chiral exciton, it is excitation in a semiconductor nanoparticle. So in semiconductors, in molecules, we just excite molecule, promote 1 electron from this lower state to the upper state. And this exciton is more or less localized, maybe on 1 molecule and a few molecules. Here in nanocrystals, our exciton, which is called now Wannier mode exciton, is delocalized in the whole structure. It's moving on the size of a few nanometers at least. So mathematically it becomes different. Quantum mechanics becomes different because of the band structure. And so if our crystal has chirality, intrinsic chirality, because lattice is chiral, this is helical motifs of atoms. It is actually mercury sulfide, it can be also telluride. Then wave function of exciton will be chiral in circle.
That has like an angular momentum?
It's kind of angular momentum. But it's not simply angular momentum because simply angular momentum may be non-chiral. It means that potential in some way is helical. It's a helical potential that the electron feels. And then the wave function become chiral. And another chirality in this nanoparticles, the shape is just chiral. So we create such twisters, for example. And then wave functional is also chiral, so circle dichroism should appear because of the symmetry and because of the quantum mechanics.
Second question. In the beginning that you have like a 2 nanoparticles. There's a molecule in between that has a theory about that. So what did you put in there?
For what is input? Input is very simple. It is, we take two spheres.
Yeah.
Two spheres, either silver or gold. We take the electric functions from the tables, from the experiments. And then we place dipole, chiral dipole, molecule, two-level basically system in the middle. And we calculate absorption. And it is important that we calculate interactions between the dipole and the spheres. And interaction is very strong because this is strongly polarizable things. This can be done in different methods, actually, either semi-analytically or on CAMSOL or.
Sure. Very short. Do you have any scaling relations for the observable chiral signal from, say, this helical arrangement of gold nanoparticles? How does the observable dichroism, say, depend on the pitch relative to the size of the particle?
Yeah, we had lots of such scaling things. Basically, this simple for systems which are not very large is this. Larger nanoparticles, more interactions. Of course, this is valid only when they don't touch. So the smaller the distance, the better, because interaction is strong. Then pitch should be optimized. If pitch is very long, it will be almost line. No chirality. If you squeeze it, it will be, they become touching.
So what is the optimal?
Optimal pitch is when the distance to the center is about the distance to the radius is about the distance between two particles. It may be some coefficient. We calculated it. So they should be comparable. So pitch and radius should be comparable to have the maximum optical chirality in this circle dichroism. The last one.
I think when you, I have to say no. Because we have
Okay, no comment.
You should blame me, I talk a lot.
I suggest that we could, that other questions are certainly rising and there will be more. I suggest that this will be continued in the coffee break and during the lunch.
Yes, so please ask questions.
I have responsibilities to you and to the next speaker. Let's think especially